Once we've learned how to use the disk washer method and the shell method for finding volumes of revolution, a common question comes up. How do you know which method to use? In most cases, you can use either method, but one method will be a lot easier than the other. In some cases, only one method will be possible. To help us figure this out, the first thing we're going to do is draw the region and determine whether that region would be easier to integrate with respect to x or y. Then we'll draw a representative rectangle. We look at that rectangle and determine whether it is perpendicular to the axis of rotation or parallel to the axis of rotation. If the representative rectangle is perpendicular to the axis of rotation, we use the disk washer method. If the representative rectangle is parallel to the axis of rotation, we use the shell method. A quick mnemonic to help you remember this is the word perpendicular and the word parashell. Neither's really a word, of course, but clearly it's going to help us remember which method to use depending on whether the representative rectangle is perpendicular to the axis of rotation or parallel to the axis of rotation. Let's look at example 1. Find the volume of the solid generated by revolving the region bounded by the graphs of y equals square root x, y equals 0, and the line x equals 1 about the x-axis. Let's start off by drawing the region. If we were to integrate this region, it would probably be easier to integrate with respect to x to get this area here. And a representative rectangle might look like this. We're rotating about the x-axis, and we notice that the representative rectangle is perpendicular to the x-axis. So we're going to use the disk washer method. Revolving this rectangle about the x-axis would give us a disk that looks something like this. And the curve would rotate around to give us a solid that looks something like this. Our cross-sectional area is a circle, and this is the radius of that circle, which is the square root of x. For the disk washer method, we'll need to integrate the cross-sectional area. As we've seen before, this is simply pi r squared, where r is given to us by the square root of x. Now we're ready to find the volume. We're integrating the cross-sectional area, dx, and our x's are going to start at 0 at the origin, go out to 1. Integrating this is pretty straightforward. And we have a volume of pi over 2. Now let's try this using the shell method. Again, we're rotating about the x-axis, and our representative rectangle now is going to be parallel to the x-axis, the axis about which we're rotating, and that rectangle may look something like this. And when that rectangle is revolved about the x-axis, we'll get a shell that looks something like this. The curve was given to us as y equals the square root of x. But now we're going to be integrating with respect to y, so we need a function of y, so we can rewrite this as x equals y squared. First, we need the height of the shell. And in this case, the height of the shell goes from here to here. In other words, we start at 1, and we subtract from that 1 the value right there, which is going to be our y squared. So the height of our shell is 1 minus y squared. If you recall, when doing the shell method, we take the circumference times the height of the shell times the thickness of the shell. So in this case, our circumference is going to be 2 pi times the radius. In this case, the radius is y. The height of the shell is 1 minus y squared, and the thickness is our dy. And we're integrating from 0 to 1. Now we evaluate this integral. And we get to the same result. In this case, each method was roughly about the same amount of work, so it doesn't really matter which one we chose. Let's look at example 2. Find the volume of the solid generated by revolving the region bounded by the graphs of f of x equals x squared plus 2x, and y equals 0, and the line x equals 1 about the y-axis. So we'll be revolving around the y-axis like this. Now, if we were to integrate this region, we'd probably draw a representative rectangle vertically to the function. So we'd be integrating with respect to x, and that rectangle would be parallel to the axis of rotation. So we'll be doing the shell method. So when doing the shell method, we think of the word parashell. That means our representative rectangle is parallel to the axis of rotation. So we might get a representative rectangle like this. And when we rotate that about the y-axis, we get a shell that maybe looks like this. Let's get the height of the shell. Well, that's going to be this distance here, which is simply the vertical distance to that curve, which is y equals x squared plus 2x. The radius of the shell is x, and it's going to range between 0 and 1. So using the shell method, the volume is equal to the integral of the circumference of the shell times the height of the shell times the thickness of the shell. So once again, 2 pi times the radius, which in this case is x, is our circumference of the shell times the height of the shell times the thickness of the shell, which is dx. And we're integrating from 0 to 1. And we get a final result of 11 pi over 6. Now let's try the disc washer method. So if we were to draw a representative washer, it might look something like this. And to find the cross-sectional area, we're going to need to find little r, and we're also going to need to find big R. First off, notice that big R is constant. Big R is always 1 because it's the distance from the y-axis to the vertical line x equals 1. But little r changes depending on which y value we have. Down here, little r is relatively small. Up here, little r is relatively big. So to find little r, we need to solve y equals x squared plus 2x for x. In other words, we need x as a function of y because little r changes with different values of y. To do this, we'll subtract over the y and get all of this equal to 0. And then notice that we have an equation quadratic in form, where a is the leading coefficient of 1 in front of the x squared, b is the coefficient in front of x, which is a positive 2, and c is the constant in back, which in this case is negative y. Now we use the quadratic formula. And then simplify. Since r is a distance going into the first quadrant, we want a positive value for x. So we'll choose x to be negative 1 plus the square root of 1 plus y. That is little r. Now we're ready to integrate using the dishwasher method. The y's range from 0 to 3, and we're going to take pi capital R squared minus pi little r squared, in this case dy. We can factor out the pi. Capital R is 1, so 1 squared is just 1, minus our little r squared. Simplifying this, we get pi times the integral from 0 to 3 of 2 square root of 1 plus y minus y minus 1. Now we integrate. And we get the same final result. So in this case, the shell method was considerably easier. The tricky part was rewriting our function of x as a function of y. Sometimes that step's impossible, and we have no choice, and we'd have to use the other method. Let's look at example 3. Find the volume of the solid generated by revolving the region bounded by the graphs of f of x equals 1/2 plus x squared and g of x equals x over the interval 0 to 2 about the x-axis. So if we were to find the area of this region, we probably would take the top function minus the bottom function and end up with a representative rectangle that looks something like this. We're rotating about the x-axis, so we have a representative rectangle that is perpendicular to the axis of rotation. So we're going to use the disk washer method. A representative washer might look something like this. We have little r and we have big R. Our top curve here is y equals 1/2 plus x squared, whereas our lower function is y equals x. So big R is the distance from the x-axis to that parabolic function, which is going to be 1/2 plus x squared. Little r is the distance from the x-axis to that line, which is just plain x. So using the washer method, the volume is going to be the integral from a to b of pi capital R squared minus pi little r squared, and in this case we're integrating dx. Here our x's go from 0 to 2. We can factor out a pi, and we're going to end up with capital R quantity squared minus r squared dx, like that. We'll go ahead and simplify this. And then integrate. And we end up with 69 pi over 10. Now, what would happen if we tried the shell method? Our representative rectangle now would be parallel to the axis of rotation. So we might have a representative rectangle that looks like this. And that's going to work just fine as long as we are above 2. Because if you notice, this particular rectangle is going between our parabolic function and the vertical line x equals 2. But if we go below 2, about here maybe, now we have a representative rectangle that's going between the parabolic function and the linear function y equals x. But then it changes again below this line, which happens to be 1/2. Here, a representative rectangle would go between the linear function y equals x and the y-axis. So this means we're going to have 3 different regions on which we're going to have to apply the shell method. That means we're going to have to integrate 3 different times. We'll call this region 1, region 2, and the small one at the bottom, region 3. We're going to be integrating with respect to y, so we're going to need the limits of integration. In other words, we're going to need the y values at each of these points here. Since the parabolic curve is 1/2 plus x squared, we have a 1/2 here. Plugging that into our linear function y equals x, we know this point is 1/2 comma 1/2. Similarly, this point here has an x value of 2 and it's on the line y equals x, so this point is 2 comma 2. And then finally, the point up top is 2 comma, plugging that into our parabolic function, we'll get 9/2. So our 3 regions will be 1, y values ranging from 2 to 9/2, and we're going to have to figure out the height of those shells. Region 2 is going to go from 1/2 for y up to 2. And again, we'll have to find the height of the shells in that region. And finally, in region 3, our y's are varying from 0 up to 1/2. And we need to figure out the height of those shells also. Starting with the easiest one, imagine a shell down here in our 3rd region, maybe looking something like that. The height of the shell is going to be that distance there. And since our linear function y equals x can be rewritten as x equals y, this distance is simply y. Looking at region 2, our representative shell might look something like this. And we need this distance here. Well, that's the distance between our parabolic curve and our line x equals y. Let's first rewrite our curve as a function of y. In other words, we're going to isolate x here. That's going to give us x equals the square root of y minus 1/2. So this height here, we're going to start with y and subtract off the square root of y minus 1/2. In other words, this is the distance y, and we're subtracting off this distance here, which is square root of y minus 1/2. Finally, looking at region 1, the height of our shell will be this distance here. And that's a matter of starting with 2 and subtracting off the parabolic curve, which is the square root of y minus 1/2. Now that we have the height of each shell, now we're ready to set up our integrals. As usual, when we are integrating using the shell method, we're going to take the circumference of the shell, which is going to be 2 pi y, times the height of the shell. If we look at our first region, our height is 2 minus the square root of y minus 1/2, times the thickness of our shell, which is a dy, and region 1, we're integrating from 2 to 9/2. Region 2 will be done similarly. Now we're integrating from 1/2 to 2. The circumference of the shell is going to be 2 pi y again, This time the height of the shell is y minus the square root of y minus 1/2. Thickness of the shell again is dy, plus region 1 integrating from 0 to 1/2. The circumference of the shell is 2 pi y. The height of the shell is y, thickness dy. So there we've set up our three integrals using the shell method that will give us the volume of revolution of the region given in this problem. To simplify this integration, we can factor out a 2 pi out of every single integral. At this point, we have two pretty involved integrals. In particular, we have not yet learned how to deal with integrating these functions right here. We're going to learn that in a future chapter. But the rest of the integration looks something like this. And the integration from here to here, as well as the integration from here to here, utilizes a technique called integration by parts. Let's go on to example 4. Example 4, find the volume of the solid obtained by rotating the region enclosed by the curves y equals 5 and y equals x squared minus 5x plus 9 about the line x equals negative 1. Before graphing this, let's go ahead and find the points of intersection. So our points of intersection are 1, 5, and 4, 5. From there, to help us graph the parabola, let's go ahead and find the vertex. So that's going to be at negative b over 2a. In this case, b is negative 5, so we have negative of negative 5 in the numerator, and 2a is just 2 times 1, so we are at 5/2. Finding the corresponding y value. And that's going to give us 11 over 4. So our vertex is at 5/2, 11 over 4. So there's the graph of our region, and we are rotating this about the vertical line x equals negative 1. So if we were finding the area of this region, it would make sense to draw a representative rectangle that looks like this, where we're taking top function minus the bottom function. And this representative rectangle is parallel to the axis of rotation, so we're going to use the mnemonic parashell to remind us that we're going to try the shell method. We need the height of the shell, which is going to be 5 minus the function x squared minus 5x plus 9. This shell might look something like this. Now we're going to need the radius of the shell, which is going to look something like this. Well, the distance from the y-axis to the blue curve is going to be our x value, but then we have to add on this distance here, which is 1. So we have 1 plus x. That is the radius of our shell. So when we go to find the volume, using the shell method, we're going to integrate circumference first of all. So that's 2 pi times the radius, which in this place is 1 plus x, or x plus 1, times the height of the shell, which is 5 minus the quantity x squared minus 5x plus 9, times the width of the shell, which in this case the width is a dx. And our x's are ranging from 1 to 4. And now we'll go ahead and simplify and integrate. we get a result of 63 pi over 2, and that is the shell method for this particular example. Let's try doing this again, this time with the disk washer method. Okay, so our representative rectangle in this scenario is going to go horizontally, like this. And a representative washer might look something like this. Now, little r is going to start at -1 and go to this side of the parabola, whereas big R is going to start at -1 and go all the way over to this side of the parabola. And so that means we're going to have to rewrite our function y equals x squared minus 5x plus 9 as two separate functions of y, the right half of the parabola and the left half of the parabola. In order to do that, we're going to have to take y equals x squared minus 5x plus 9 and solve this for x. And the way we're going to do that is by completing the square. We divide -5 by 2 and square it. And if we add that on, we also have to subtract it off, like that. Factoring, we get x minus 5/2 quantity squared. And we now have this form of our parabola. Now we can isolate x, taking the square root of both sides. So here you'll notice we have two different functions of y. We have x equals 5 over 2 minus the square root of y minus 11 over 4, and x equals 5 over 2 plus the square root of y minus 11 over 4. Now, just to be clear, this yellow expression is giving us this part of the graph here in yellow, and this expression here in purple is giving us this side of the graph there. So little r is going to be this distance 1 plus the distance to the yellow part of the parabola. So we're going to get 1 plus 5 over 2 minus the square root of y minus 11 over 4. Similarly, big R is going to be that same distance 1 plus the distance to the right side of the parabola, meaning the purple highlighted portion of the parabola. So we're going to get 1 plus 5 over 2 plus the square root of y minus 11 over 4. We can combine the constants in front. And now we're ready to find the cross-sectional area. So A of y is going to be pi capital R squared minus pi little r squared. So we get pi times 7 over 2 plus the square root of y minus 11 over 4 quantity squared minus pi times 7 over 2 minus the square root of y minus 11 over 4 quantity squared. Now we can factor out the pi. Now there's a couple of ways of moving forward here. We could square each part and then subtract, but an easier way to go is to notice that we have a difference of squares. We've got a squared minus b squared, which of course can be factored this way. And this is our value A, while this is our value B. So we're going to take the sum of these two and then the difference of these two and multiply them together. So we have pi times, we need our A minus B, so that's going to be 7 over 2 plus the square root of y minus 11 over 4, there's A, minus our B, which is 7 over 2 minus the square root of y minus 11 over 4, like that. And that's going to multiply our A plus B, which is 7 over 2 plus the square root of y minus 11 over 4, plus 7 over 2 minus the square root of y minus 11 over 4. Like that. Now we get some nice cancellation. So we'll end up with subtracting the negative root will give us 2 of those roots. So we have 2 square root of y minus 11 over 4. And then in back, the square roots cancel off and we get 7 over 2 plus 7 over 2, which is simply 7. We can rewrite this as 14 pi. And for the square root, I'm going to factor out a 1/4, writing it this way. And of course, the 1/4 can come out of the square root as a 1/2, and we're going to be left with 7 pi square root 4y minus 11. So that is our cross-sectional area. Now we're ready to integrate it. So to find our volume, we're going to integrate our cross-sectional area, which is 7 pi square root of 4y minus 11 dy. Let's double check to see what the y's are starting at and going to. If we look at our original graph here, we're starting here at the vertex and going up to 5. Well, we found the vertex a while ago to be 11 over 4, so we're integrating our y's from 11 over 4 to 5. We can factor out the 7 pi. And now we'll go ahead and reverse engineer our antiderivative. So I know I'm going to have the 4y minus 11 raised to the 3/2 power because I'm adding 1 to the exponent. I'm going to need a 2/3 in front. But when I take the derivative of the inner function, I'm going to have an extra 4. So here I'm going to need a 1/4 to balance that out. And we're evaluating this from 11 over 4 to 5. Again, pause here and take a derivative. If you take a derivative, you're going to leave the 7 pi on the outside. You're going to take the 3/2 multiplied times the 2/3, so that gives you a 1. Subtract 1 from the exponent, you have a 1/2. Then you have to multiply by the derivative of the inner function, which is 4 times the 1/4. It should take you there. We can simplify a little further. The 1/4 and the 2/3 will give us 1/6, and we can bring that out to get 7 pi over 6. And then we're just evaluating 4y minus 11 to the 3/2, evaluated from 11/4 to 5. So we end up with 7 pi over 6. We plug in a 5 there. We're going to get 20 minus 11, which is 9 to the 3/2. And plugging in 11 over 4 is going to give us 0, so we're just left with this. The square root of 9 is 3. Raising it to the 3rd power is 27. And we cancel to get a 2 here, a 9 there, which gives us 63 pi over 2. So there is the disk washer method for this particular example. Now, as you proceed through the problems in the rest of this worksheet, don't do both methods. First, draw the region and choose which method is easier by first figuring out what the representative rectangle would look like. Decide if it's parallel or perpendicular to the axis of rotation. If it's perpendicular, you use the disk washer method. If it's parallel, you use the shell method. If you start one method and it seems way too complicated, maybe try the other method. Go ahead and try the rest of the problems.